Today we'll start our discussion of high frequency analysis. So far what we've done has been basically focusing on low frequency circuit analysis and things where you have resistors, dependent current sources and voltage sources, independent current sources and voltage sources, but no element with dynamics. Basically we ignore the effect of capacitors and inductors and things of that such. So now we'll talk about some of the general properties of the system with the dynamics. So the dynamics part is actually the part that's very interesting and carries a lot of information. And what we'll do first, we'll review some of the general concept to make sure that everyone's on the same page as far as the concepts of high frequency analysis is concerned, the LTI analysis, and then we'll go and do the actual, we'll start talking about the method of time and transfer constants, which is a method to determine the transfer function of the circuit basically by doing a bunch of low frequency calculations. Okay, but before we do that, let's talk about the general properties of a system, right? So let's say you have a single input, single output system. So you have x of t coming in and y of t going out. And let's say this is your system and we show it as an operator operating on this thing, right? So this is the system. We want to see how we can characterize this system. Now, in time domain, of course, if you have a time domain signal coming in, you have a time domain signal coming out, and that's in general what the system does. The system, in most general case, could be nonlinear, could be time varying, and will have dynamics. So the question is, now, what do we do with this system? So if you had something like this, and let's say the system were linear, we want to see what we can say about it. Now, if we can also look at frequency domain picture of this thing. And to do the frequency domain, we can basically use the Laplace domain. So basically, the Laplace transform, just to refresh everyone's memory, is defined as such. So basically, it's x of t et minus st dt. So this is the Laplace transform of the x of t, which basically sometimes is shown as the Laplace transform of x of t. So in Laplace domain, in a frequency domain, so this is a general frequency domain, right? X of t, and then you have an output that's like general y of t, y of s, and x of s. And of course, you know that if you want to go to the kind of frequencies that we typically talk about, what you really have is basically you can evaluate it on the j omega axis and with kind of sinusoidal frequencies. And we'll see what the general s complex frequencies mean. So this is basically a complex quantity. So now if you have something like this, then I'm interested in determining what the y of t is in terms of x of t. Now I know one thing, in time domain, x of t can be written as using the shifting function in terms of the Dirac delta. So you can basically always write x of t in this form. An integral from minus infinity to plus infinity of x of tau, x of tau, delta of t minus tau, d tau. There are different ways you can interpret this, basically. So Dirac delta functions are basically functions that are approximations of a pulse when the pulse becomes very narrow. So the property of the Dirac delta is that it has an area of 1, so basically integral of Dirac delta dt plus minus 0 to plus 0, a little bit before 0, a little bit after 0, is 1. Right? This is the property of the Dirac delta. And you know delta of t is 0 when t is not equal to 1, to 0. Right? So you can interpret this different ways, several different ways. One way to interpret this is that you can say, okay, this is a shifted delta. So delta of t minus tau is a delta that sits here. So basically it takes a sample. So you say, I can represent my signal as a table, this is the table, of its values. And each value is weighted by the deltas, so basically I'm putting these deltas of different values next to each other. Of course it's a continuous thing, so what I'm saying is a continuous and uncountable kind of thing. But this would be representing the signal. So this is basically another way of thinking. So this is a table of values in a way, if you think about it. Okay. Another way to think about it is that you can think about this as these are basis functions for the signal. So these are bases that you can use the function. So now, either way, whatever it is, this is basically a representation of x of t. You can always write it this way. Now, the good thing about it is that if you're thinking about this as a table of values, these are not functions of t anymore. These are values, but constants per per se, if you want to think about it in that domain. Now, the question is, what does the system do on this, right? So now the system is up, the system operator is acting on this. So now the system comes in and says, okay, I'm operating on this. What will happen? Well, it depends on the operator. Now, if this operator is linear, and not necessarily time invariant, just linear. So if it's linear, so in other words, your system is linear, what happens is that it allows you to switch the order of summation and the operator. So the operator operating on sum or an integral essentially is equivalent to the integral of the signal operated upon. Now the operator is a function of t, so the only thing it will operate on is this. This is d tau. So the only thing it will operate on will be something that's function of t, which is this thing. So you can just write this instead as integral of minus infinity plus infinity x of tau, the operator operating on the delta of t minus tau d tau. Okay? And this, in general, is the response of the system to an impulse at time t equals tau. So this is the response of the system if you have an impulse at time t equals tau. What comes out of the system is this thing. And in general, it's shown as minus infinity plus, as x of t and tau. H of t and tau. And this is called the general impulse response of the system. This is valid for time-varying systems. Basically what it does is that it basically is valid if the system properties change with time. They don't have to basically remain constant. So the system can have a different response now from a microsecond later. And still you can do it because this is, if you think about it, it's a function of two variables, right? It's a function of t, it's an impulse at any point in time. So this is the table of responses. So it's a table of responses. So it says for t, tau equals 0, it looks like this. For tau equals whatever, 1, it looks like that. Something else, some other shape. Right? So it's an infinite number of different responses. Now, in general, so this is basically valid for a time-varying system, but linear. So this is very valid for linear, time-varying, and time-invariant as well. But valid. And this is called the superposition integral. Some people mistakenly call this the convolution integral. This is not the convolution. This is the superposition integral. The convolution is the one that comes next. Now, let's assume that the system is not only time-invariant, linear, but also it's time-invariant. In other words, its response is the same today and tomorrow and any other time. So if I hit it with an impulse today, I get a response that looks a certain way. If I hit it with the similar impulse tomorrow, I will get exactly the same response, of course, delayed by 1 day. It has to be, right? Otherwise, it doesn't make sense. So whenever you hit it, you get the same response. In that case, all of these functions will look the same. They're only shifted with respect to each other. So instead of being a function of two variables, they become a function of one variable, which is basically the difference, the time between the actual time and the time of application, which is t minus tau. So in that case, basically, if your system now is time invariant, then this becomes a function of single variable. So as long as you know h of t, the impulse response to a single impulse at time t equals 0, you know everything about the system basically. All you need to know is basically to know h of t. And if you know h of t, you can always use integral to determine response of an LTI system. So this is LTI, because linearity was already assumed. To an arbitrary input. So y of t can always be calculated using x of t for this. So all you need to know is this time domain signal. Now, okay, so this is a very useful thing. This is called the convolution integral. frequency domain. If I take this to frequency domain and basically take the Laplace transform of both sides, what you see is that in frequency domain, of course, this side will be the Laplace transform of this, which basically is y of s. And then on this side, I have to take the Laplace transform of this. And when you take the Laplace transform of two things being convolved, it's very easy to see. Basically, it's just you need to plug this into that definition to do a single change of variable. And what you see is that it becomes the product of the Laplace transforms of these two. In other words, it becomes x of s times h of s, where h of s is the Laplace transform of the impulse response, h of t. And by the way, this can also be written in the following form sometimes. The convolution, as you're familiar, I'm sure, can be written as x of t convolved with h of t. So in frequency domain, it becomes a product. Now, what this allows you to do is to define what we call a transfer function. The transfer function is simply the ratio of the output in frequency domain to the input signal in frequency domain. And it's nothing but the inverse Laplace transform. Actually, it is the Laplace transform itself, the Laplace transform of the impulse response. Now, you can see this looks very much like the kind of signals that we have been dealing with at low frequency, in the sense that the gain was similar to that, right? It was a ratio of something in the output to something in the input. So it's a generalized gain, except for the fact that these are now functions of frequency. So as long as you do it in frequency domain, this is fine. And the good thing is that now if you have your transfer function, which is something a lot of times for kind of circuits that we analyze, easier to calculate than the direct impulse response, you can easily calculate, of course, the impulse response, which basically the time domain impulse response would be the inverse Laplace transform of the transfer function. Now, this is a very important thing. Basically, this is the important result that comes out of this discussion, which is something that you already knew probably, most likely. You've had it in your previous courses, and this is nothing but a review. But it essentially says that you can define, or another form of writing it is this. Which is the transfer function is the ratio of the output signal to the input signal in frequency. So we use this, if you use the similar techniques that we use to calculate the gain as a function of frequency, then we can determine the transfer function as a function of frequency. And of course, if s equals 0, this becomes like basically the low frequency gains that we've been calculating so far. And then, if you know this, you can always calculate your Laplace, your impulse response and do a time domain analysis, if you will. The other interesting thing is that, of course, you can calculate your y very easily by calculating the product of the Laplace transforms of the input and the transfer function, and take the Laplace transform of the output signal to get the result that you need. Okay, any questions on this? So now, if you have a transfer function, you can define a transfer function. Now, what can we say about the transfer function itself? A transfer function of a system, you can show that the transfer function of a circuit consisting of lumped elements, namely elements that are like two terminals, much smaller than the wavelength as we defined them before, can always be written in a fractional form. So the transfer function of a lumped system can be always written in the following form. So, and where the coefficients are real. second-order polynomials with real coefficients. Or another way of saying it is that you can factor it in as product of first-order polynomials whose coefficients are either real or come in complex conjugate pairs. Because if you have a second-order polynomial, you can factor it always as a product of two first-order polynomials with complex conjugate pairs. That's a quadratic equation, basically, right? To solve a quadratic equation. And if it couldn't be factored in two real parts, it means that the roots were complex. So in the most general case, this can be written as in the following form. If you factor A0 out, which is what is A0, by the way? A0. It's the DC gain, right? It's the DC transfer function. If the transfer function is a gain, then it becomes a DC gain, exactly. So if you do that, then you can write it as 1 minus S over P1. Oh, I'm sorry, over Z1. 1 minus S over Z2. All the way to 1 minus S over Zm. And then in the denominator, you will have 1 over S over P1, 1 minus S over P2, all the way to 1 minus S over Pn. Now, the roots of the numerator are called the zeros, as you know, and the roots of the denominator are called the poles. And they are in general complex quantities. So they can have a broad range of values. Since these coefficients are real, but if they are complex, they are always coming in complex conjugate pairs, where they have the same real part and imaginary parts that are of opposite polarity and same magnitude. So that's the general form of writing a transfer function. That's not the unique decomposition or factorization. There are different ways to factorize this, and I'll show you one more example that would be useful. But let me ask you a couple of questions about this. So let's think about this and think that, okay, so if we assume that this is the gain or the transfer function of an amplifier, a real amplifier, what can you say about the number of poles with respect to number of zeros? If this were a real actual amplifier, physical amplifier, right? Can you say, can I have more zeros than poles? Well, just by looking at it. Why not? See a lot of people shaking their hands. Their heads, I guess. So, what happens if I have more zeros than poles? Well, what would the gain be? If I had, basically having more zeros than poles means that the order of numerator is higher than the order of denominator. And if that's the case, it means that at infinite frequency, what would the gain be? Infinity. And since practical real amplifiers don't have infinite gain and infinity, at infinite frequency, then we know that we can practically have more zeros than poles. Can we have the same number of zeros and poles? For a practical amplifier, it's unlikely, right? Because it means that we'll have non-zero gain at infinity. But a lot of things that we model, the way we model them, since they don't capture this higher order small capacitors or inductors that we have somewhere else that will eventually kill the gain, or things that where the model represent the failure of the model, may have we will see things that we have equal number of zeros and poles. But we'll keep in mind that there must be some practical physical thing coming in that we haven't modeled. Either our model is incomplete, or we simply have not modeled it, that will cause the gain to drop at high frequency.
Quick question. Is that saying the same thing as, because even if the orders of the numerator and denominator were different, you could say there's a zero at infinity or a negative infinity, and then you could say that the number of poles and zeros would be equal.
Okay.
Is that saying the same thing?
Yes, that's a good, okay, so that's a good distinction to make. So basically when I talk about zeros and poles not being equal, I mean the number of zeros and poles, the finite zeros and poles. You can always assume that there are enough poles and zeros at infinity to balance the number of them. And that's another way of saying that you have gain at infinity or something like that. But yeah, so we can sometimes say, okay, well, our zero is at infinity. Basically, some other times we basically say we don't have a zero. When we say we don't have a zero, it means that our zero is at infinity. That's not exactly what we say here. So this representation, what you see here, if you actually look at it, you can try to look at these and look at it on the so-called Bode plot, right? You can try to evaluate it on a Bode plot, and we'll do that. But before we do that, let's even certain kind of transfer function of certain poles. So let's now think about systems with one real pole or a pair of complex conjugate poles. And we want to see what the transfer function, how the transfer function is related to the impulse response. So let's think about where the poles are in the complex conjugate plane. So this is the S plane. So this is sigma, the real part, and this is j omega, the imaginary part. So let's start with something that, let's say I have a system that has a single pole at 0. So this is a single system, a system with a single. So basically, I'm saying that h of s is 1 over s. Or it could be some constant type 1 over s. Right? So, what is the impulse response of this system? Basically, by saying that I have a single pole in this diagram, I'm basically telling you what the transfer function is. Right? Within a constant. Within a scalar factor. Right? So, what is the impulse response of this thing? How does it look like? Unity. No, well, it's a step.
Oh, yes.
Right?
Yes.
It's so the impulse response, h of t, looks like this. It's a unit step function. Right? And again, this should be obvious because this is an integrator, right? You're integrating the delta from minus infinity to t. Now, if your delta, if t is smaller than unity, smaller than 0, then you don't catch the delta. So basically, your integral is 0. You're integrating 0. When you go beyond, at this point, you have an area of 1. Your delta has an area of 1, and therefore you go to 1. And this is another way of saying and showing an ideal integrator. This is an ideal integrator, right? So now, what if I have a pole? Let's say now my transfer function, instead of that, is a system with a single pole, whose frequency is here. Right? Let's say at this time. So it's basically at this value. What does the impulse response look like? So what's the impulse response? So basically I'm saying at h of s, so another way of saying this is like minus s over p. So it looks like that, p1. What does this system have? What kind of step response do you have? You have an exponential, right? So you will have an exponential like that. And it reaches 1 with a time constant tau, which is minus 1 over p1. Now, what if the pole is here? We're here. What if we're farther down here? Let's say p. So this is now instead, so I have still a single pole system, right? This is just, I'm changing the frequency. So what happens? What is the, how would this impulse response look like?
Time constant is much larger.
Hmm?
The time constant is much larger. Time constant, so
Right. So the time constant of this thing would be larger or smaller?
it's smaller.
This is a higher frequency pole, right? This is 0 and going up in frequency. So this will have a faster response. Is that correct?
Why are you
No.
not decaying?
No. Okay, that's right. This is not correct actually.
Negative real power, right? So it should be decaying.
Right. So actually, what you see here, correct, this is not the right response. This is the right response. So what this does, if you have a pole here, then you basically have a tau minus 1 over p1. And this is 1. So it should be decayed. Because at infinity, what do you get? And yeah. So it basically should decay like this. And then this guy should be decaying faster. Correct? So this is tau 2, which is minus 1 over p2. And this will be decaying faster. So what happens here is that if you start with a pole here, if you have a pole at the origin, you get something like that. And then if you have a pole that's down here, then you will go up and then you will drop down. And then the farther out the pole is, the higher frequency, the faster it drops. Because if you think about it, what happens if the pole were at infinity, or minus infinity? It basically is as if the pole is not there. So what should the impulse response be? An impulse, right? It should be the same. So in the limit, it's reaching a very sharper and sharper pulse, so eventually it becomes an impulse. In the limit going this way. Now in the limit, guy, this time constant is becoming longer and longer and longer. Basically, it becomes infinitely long. So it becomes constant. So this is basically a time constant of infinity, whole frequency of 0. Right? So now, so this is our point. These are basically poles with negative real value. So what if I had positive real value? What would I get? So think about it. Let's say I have a pole here. I can have a pole there. Right? So let's say my response of the system corresponds to a positive pole. So basically that's a plus sign. Or P, basically, yeah. So what happens? Well, again, you can probably even extrapolate from thinking this way, right? And just like if you think that, see the progression. So all the way out here, you had the impulse response was the impulse. And then you gradually become slower and slower and slower to get there. And then what should happen? Then here, you will see it growing exponentially. Something that's exponentially growing. And the farther out you get, so let me just do this in a different way. And if my pole were here, then I have an exponential that's growing even faster. Does that make sense? So these are the impulse responses of the system. So you can create a time domain, frequency domain relationship or correspondence. Now, what if I had complex conjugate, not complex. So let's start with a set of poles that are complex, but let's say they're purely imaginary. So let's say I have a set of poles here, and then of course they have to come in complex conjugate pairs, right? So now I have a second order system. So let's say my system is second order system. What is the impulse response of that system? If they're exactly on the j omega axis. So it's a sinusoidal thing, but it's not going to decay or grow, right? So it's going to be basically just a sinusoidal response. So you go there, you will remain there. Now, what happens if these poles were closer here? Let's say there and there. What will you see there? You should see it. So it's a smaller frequency. So basically the sinusoidal of the frequency of the sinusoid should be smaller, right? So it should be like more like this, the response of the system. And you can see again in the limit, if you bring these poles closer and closer to this point, you're approaching this guy. Because it becomes so slow eventually that you don't see any of the sinusoid, and you just basically see this could be the beginning of a very, very, very slow sinusoid, right? I could have said this like. So you can see it has to be continuous. I mean, you can't have a qualitative change in the behavior. Now, what if I have, so fun. So what if I have a pair of complex conjugate poles, let's say here? What would that do? It would be a decaying sinusoid, right? So what happens is that the impulse response will look like this. Well, jumps up to the peak value, but then it decays. Now, what if these poles were farther out? To the left. Decays faster. But not the frequency. The frequency of the sinusoid is not going to change. It's just going to be more difficult to draw. So the sine part, the cosine part of it will have pretty much the same frequency. But it will decay faster. So it's decaying faster. And if it were, let's say, if the poles were down here, what would you see? Let's say they were down here. So they have the same real value, but the smaller imaginary part. The decay rate would be the same, but the sign would become slower. And if they were farther out, the sign becomes faster. What if they were on this side? What if I had a pair of complex conjugate poles with a positive real part? Yeah. So I will have the sinusoidal response, but then it would be growing. I guess the frequency needs to be similar to that, but that's, yeah. we'll talk more about this. And we'll talk about the effect of zeros when we get to this. Now, this picture, mental picture, allows you to kind of visualize what the impact of these individual elements are. Individual parts of this thing. Any questions so far? No? Okay. So, if you look at this, so let's go back to this picture that we had, the representation that we had. And we can express A1s and B1s in terms of poles and zeros. So that's also something important to keep in mind. So, what is B1? If I ask, what is B1 in terms of all the poles? So let's say I tell you where the poles are, and you want to know what that coefficient B1 is. How would you determine that? Well, you can see. You get the first order term in S only from the product of individual terms like that with all the remaining ones. And you always get a minus sign. So B1 is obviously what? It's going to be the sum of all the poles, free time constants, right? So it would be I equals 1 to n. Agreed? Because if you just multiply it out in this form, right, you will see that only taking one of these with all the remaining ones gives you the first order terms. And every one of them will have a minus sign. So what is B2? Now B2, you have to take two of these with all the remaining ones, right? And of course the minus signs cancel each other. So you get double sums, and we have to define 1 over pi pj. So now the indices I have to be careful about here. And this is, just pay attention to this because this kind of indices will write several times in the future. So you have to be careful. So let's say I going from 1 to n. Okay? Or n minus 1 actually. And let's say j goes from I plus 1 to n. This way you avoid 1, 2, and 2 1s. You get only one of them, right? Because this guarantees that j is always greater than I. So you get every combination this way as long as j is greater than I. So if you are getting P1, 2, you won't get P2, 1 if you write it this way. Now, from now on, actually I write this in a different way. Instead of this, basically in a more economical way, or at least hopefully more intuitive way, I write it like this. Ij, I say I smaller than j, smaller than equal n, and I greater than equal 1. So this is what I mean when I write it that way. When I write this, and you will see this often in the future, when I do these sums. That's what I mean. Basically, I'm avoiding doing it twice. I'm just doing one of them. 1 over pi, 1 over pj. And we can go down all the way to bn. What is bn? Bn is actually relatively straightforward. What is the nth order term? What's the one that has s to the power of n? Okay, it's the sum of pi, basically it's just the product of all of them, right? P1, P2, all the way to Pn. You can write it as the product of Pi. But then, what is the sign? Is it positive plus or negative minus? It depends, right? So it's basically minus 1 to the power of n. If n is even, it's plus. If n is odd, it's minus. And you can write exactly the same things for the a's. So I can write the a's just to complete this here. So this would be m, 1 over zi. Sorry. And this would be a1 over a naught. Sorry. This would not be a1 over a naught because I've factored a1, a naught out. Right? I factored it. So everything else becomes a1 over a naught, a2 over a naught. So a2 over a naught becomes sig double sum ij, I smaller than j. And sometimes I may be even more economical by not showing 1 and n. Or in this case 1 and n. But for now I'll show it. But you will know what I mean. Hopefully with it. And I guess a n over a naught would be minus 1 to the power of m. Z1, Z2 all the way to Zm. Okay? Does this make sense? So these are the products. So it's good to be there. have these product definitions. So what does this mean? What do these mean? How do we represent these transfer functions? That's a question, right? We need to answer. You have to think about them. And that goes back to Bode plots. Again, it's a review, quick review thing with you, for you. But just make sure that we are all on the same page of what Bode plot is. Bode plot is basically a plot of the logarithm of the signal, the transfer function, when S is basically j omega. It's evaluated, transfer function evaluated, the transform evaluated on the y-axis, on the j omega axis, and its magnitude, and logarithm of that on a logarithmic frequency domain x-axis. So what you're doing really is that you're looking at h of j omega. Basically, you're saying S is equal to j omega. In other words, you're evaluating it on the imaginary axis, and you say, okay, I'm plotting the magnitude of this thing and the phase of this thing. Well, this would be depending on what kind of transfer function it is. So let's start with the 20 log of h of j omega, and versus a log of frequency, log of omega. And then you also look at the phase of h of j omega and plot that on the same versus this. So for instance, you may have something that looks like that, and phase transfer function looks like that. Okay. Now, why 20 log? Does anyone know where that comes from? Or even 10 log? What is with the 10? Why do we plot it? And the units of this, of course, are dBs or decibels. Right? So a decibel of something is basically, by definition, is defined as 10 log of that thing. That thing in decibel. That quantity. Why do we use unit 10? Why do we have the factor 10?
That's voltage gain.
No, it has nothing to do with voltage. Basically, I'm saying that if whatever quantity measured in decibel, you can measure sound, strain, or magnitude of an earthquake, or something like that in decibel. Right? So kind of like it's actually this has to be unitless quantity to be able to, for you to be able to take a log. And if it isn't, you have to scale it by something that's unitless to make it unitless. So for instance, if you want to measure power, you may scale it by 1 milliwatt to make it a dBm or something like that. So why the 10? Where does the 10 come from? What's with the 10? Why don't we just like do that?
Historically, because of sound.
So what about?
They started to use decibel for sound, and the scale I think was 0 to 200 for reasonable.
But why that? So the actual unit. So it turns out that the actual unit is, if you think about it this way, the actual unit is actually bell. So, well, what is this thing? It's a deci. So it's 1/10 of a bell. So to make something, so actually something in bell, x in bell, would be simply just log base 10, of course, of x. Right? So x in bells would be that, without the 10, which makes more sense, just because it's a log. But then they said, well, bell is a large kind of unit. It's like a, when you say you measure things in picofarads and nanofarads as opposed to like farads, right? So you say, well, we measured it at that point, they didn't have that much of an order of magnitude, so they basically said that, well, decibel is an easier unit to deal with. It has finer granularity. I don't have to use decimal points all the time. So when they went to decibels, and they used this. Now, and it's a measure of power ratios, right? Now, but if you're dealing with things like voltages or currents, then to get the power, you always get, if you have a voltage, let's say V, across a resistor, the power across that resistor is V squared over R. Okay, at an instantaneous power. So you have a factor of 2. So basically, if you look at the voltages, your V, to get to the power, you have to have V squared. So that square comes back and makes this 20 log. So whenever you're dealing with voltages and currents, if you write it this way, then it's basically on the same scale as the power. Now the point of this thing is that, and basically this is called a Bode plot. This plot of magnitude of phase. Now the point of a Bode plot is, what is the point of the Bode plot? Why do we do Bode plots? The main point of a Bode plot is that there are several advantages. One is that you can measure it experimentally. It's very easy log of that quantity, you take a point. You make a point on the logarithmic axis. So basically, this is 20 log of that ratio of y to magnitude of y to magnitude of x. So you make a point at that frequency, at the log of that frequency. And then you can measure the phase difference. You can see what's the phase of things that are going in, the phase of the thing that goes out, and what's the phase difference. And that gives you a point on the plot. And then you change the frequency, and then you get another point. And then you have your phase and amplitude transfer function, right? So it's very easy to verify, determine experimentally. The other interesting property of this thing is that if you think about cascaded systems, so let's say you have a couple of systems cascaded, H1 of S, H2 of S, you can have multiple ones, like let's say H N of S. In other words, the output of this one goes to the input of the next one, and so on and so forth. So if you have multiple systems cascaded, what happens is that you go through the systems, and what is the overall transfer function of this system? It's a product of them, right? So the overall transfer function is going to be H1 of S times H2 of S times Hn of S. Now each one of them has its own poles and zeros. So what can you say about the magnitude of the transfer function? The magnitude would be the magnitude, the product of magnitude, right? So if you have H of j omega, this would be H1 of j omega times H2 of j omega, etc., all the way to H magnitude of Hn of j omega. Now, if you do a logarithm of this, what happens? Then it becomes a sum. The logs of these things, 20 logs of these things, would be added with the sum. So what it tells you is that if you have a cascaded system, you simply can add the magnitude parts of these to get the response, the Bode plot of the magnitude response of the overall system. Now, the same thing is true about the phase. You can actually show that the phase of H of j omega is going to be the mag phase of H1 of j omega plus the phase of the H2 of j omega all the way to the phase of Hn of j omega. Which means that the phase parts add too. So the good thing about the other advantage of Bode plots is that they add. For cascaded system, they simply, both the amplitude part and the magnitude part and the phase part simply add to each other. So the compounded overall response of the system can be evaluated like this. So anyway, so that if you have Bode plots and things like that, so basically we do a lot of Bode plots to determine things. And on a Bode plot, a transfer function like this would have the following form. So you will have basically, so you have poles and zeros and poles and zeros, and then basically you have some transfer function that looks like that. And you have it. The bottom line is that this form is very suitable for where you have a gain, a DC gain like that. Correct? Because if you have a constant, well-defined DC gain, then this is a good form to write it. For instance, if you have a DC coupled amplifier, let's say, or differential amplifier, or something like that, which has the same gain even at very, very low frequencies. For something like that, this is the right form to write it, because then you separate the DC gain from everything else, and then everything else is essentially like the dynamic. So this is the static part, and this is the dynamic. Now, but not every amplifier is like that, right? We saw another example when we were developing that discrete design example that we did a couple of lectures ago. What we did was that we basically put, in that case, we had coupling capacitors and bypass capacitors, right? Which basically made the gain very small at low frequencies. Basically, at DC, it made the gain zero because the input was detached from the amplifier and the output was detached from the amplifier through a capacitor. Do you remember that? So, in that case, this form is not very useful because what would A0 be if you were to force it into this form? A0 would be 0. Then you have a 0 times something that probably would be infinity, and then it doesn't look very good. So how would you write it? Well, there's another form. You can rewrite this in a different form. You can rewrite it in a form that wouldn't fit here. So let's see. So let me get rid of these. poles and zeros down here, and poles and zeros up there. And what is the gain that matters in this case? What is the parameter that you try to capture that doesn't depend really on the dynamical elements? If you have designed an amplifier that's well designed, then you will have a range of frequencies over which the gain is more or less constant in the midband, right? It's this gain that matters. So you want to factor that out and then say, well, it's this low frequency element times all these other things that capture the dynamics. So in that case, we define this as a midband as opposed to a zero. Mid for midband, the low band and high band. And there will be two frequencies, like omega L and omega H, the 3 dB cutoff frequencies at which this happen. And we'll determine these as we go forward. We'll see how to determine these. But now, if I can rewrite that expression in the same way. So I can write this as a mid time. Now, I will break them up into two parts. One part that captures all the stuff that happens at low frequency. These poles and zeros. These guys. And a part that captures all the high frequency stuff and separate them. And this allows me to analyze them separately later on. So, for the stuff that I have in high frequency, I will maintain the same form, right? So it could be S over ZK plus 1, because there are K of them down here. 1 minus S over ZK plus 2, all the way to 1 minus S over Zn. Let's assume that they've numbered our poles and zeros in the ascending order. So you start from the lowest frequency one and go to the higher frequency one. And then in the denominator, I will have 1 over S over Zk plus 1, up to Pk plus 1. 1 minus P of S over Pk plus 2. All the way to 1 minus S over Pn. Alright? You okay with that? Now, so that part is very similar to what was left, the high frequency stuff. How about the low frequency stuff? Now, we can write them in a better form, actually, the low frequency stuff, which is the form that's defined, is called, it was actually called by late Professor Middlebrook, the inverse poles and inverse zeros. So this is basically the way you would write it. You would just define them as Z1 over S. 1 minus Z2 over S. And all the way to 1 minus ZK over S. And 1 minus P1 over S. And 1 minus P2 over S. All the way to 1 minus Pk over S. Right? You can write it this way. So, by the way, I show them in such a way that they don't go to K. So I have the same number of low frequency poles and zeros. Why is that? Why did I do that? Because remember, poles, and we'll see this, basically the pole, what do the poles do? The poles, let's say a regular pole drops the amplitude by minus 20 dB per decade. Right? So at the pole frequency you have, basically the pole frequency at which you drop it by 3 dB. If you have a single pole, right, on a Bode plot. This is the response of a single pole system, the first order system. What if you had a single zero? A single zero would do the exact opposite. So if you had a Z1 here, this is what it does. In there, right? Now, so every pole will drop it by a certain ratio as every zero increases it. So to have a flat response here, it means that I have to have had enough same number of poles and zeros to cancel out each other's effect by the time they get to here. Right? We have low frequency things, right? So at higher system that whose transfer function was some 1 over 1 over P1 over S. Would be like that. It's the mirror image of that. And an inverse 0 looks like that. So this is a regular pole. This is an inverse pole. A regular 0. This is an inverse pole and an inverse 0. Now, what is an inverse pole in terms of real poles and real zeros? Well, let's rewrite this in a different way, right? So we can basically define a common denominator. So we can write that as 1 over S over P1, and then bring the S to the numerator. And so basically I can just factor 1 over P1 or minus 1. Basically what I have is that I have S over 1 minus S over P1. So an inverse pole is simply a regular pole with a 0 at minus infinity. At DC. No, not minus infinity, at 0 at DC. Not minus infinity. Right? So it's this combination, as opposed to showing it as 1 0 at 0 and 1 pole at the frequency of interest, we just call it an inverse pole. It's easier to deal with it that way. And this one is the exact opposite. So basically it's a 0 there at pole at 0. So it's nothing magical. I mean, it's just another representation, which is more suited for things like that. So, as you will see later on, what happens is that we come up with, our techniques allow us to calculate these poles and zeros, and these poles and zeros. There are two sets of techniques we can use to determine them separately. And if you're interested in this frequency only, then you don't have to go and write the entire thing and calculate these on the way and factor them out when you need just this, right? If you need that, you can just calculate that. If you need all of them, you can calculate all of them. Okay, so this is another representation which is more suited for like a bandpass amplifier as opposed to a low-pass amplifier. Now, another comment about the general properties of poles and zeros. So, let me ask you this question. Do you remember where the poles and zeros came from, right? Do you remember when we did the analysis, the Y matrix, right? The roots of the determinant of the Y matrix determine the pole. And they were independent of where the inputs and outputs are taken, when the outputs are taken, where the outputs are taken. Right? Because it's a property of just the network. The Y matrix is a property of just the network, not where the outputs are. So the poles only depend on the general properties of the network. While the zeros, on the other hand, would change depending on where you take your outputs. So for the same circuit, if I take the output from one node, I will get one set of zeros. And if I take it from another node, define another node as the output, I get a different set of zeros. But the poles would be the same for both of them. Would be exactly the same in both cases. Okay, so that's another thing. Now, this is just the background information we need. And basically what we can do going forward is that use this background information to use our method to take the first step. So the next thing we'll take the first step in the development of the method of time and transfer constant. So the way I will develop it here, we will develop it in steps in an inductive way. So we'll start from this first order system. We'll do the first order system first, and we'll see what it is. So we'll come up with a method for the first order system in a few minutes. And then we'll say, okay, well now we generalize it one step at a time. So we'll start from the simple and generalize till we get to the most general case. This is the way we usually learn. We start from simple things and expand. There's another way to do this analysis and learn this time and transfer constant method, which is basically the deductive way. Starting from the most general analysis and showing you that and saying, okay, well, now in the first order case it reduces to this, in the second order case it reduces to this, whatever. But I don't think that's very instructive. So we can do that, but I don't think that's the best way. Now this way you will see that how much information you can learn from just the first order analysis, and then we will do the limited second order analysis, and we'll do the expanded simplified nth order, and then we'll do the full build upon a very simple one. Any questions on this? On this material that we've covered so far, the stuff that we've talked about. So everyone is comfortable with Bode plots, right? I assume, right? You know what a pole does on a Bode plot, what the zero looks like on a Bode plot, what does phase look like, what does the amplitude of a phase of a pole look like? Everyone's comfortable with that? Good. All right. So let's take a